Com você, Nivaldo, o que quiser.
Good afternoon. Let us resume our workshop, and it's a great pleasure to introduce my friend, Professor Aurélio Menegon, and he will talk about perplex analysis from generalized Cauchy-Riemann equations to Muller fiber.
Well, thank you very much, Nivaldo. Thank you very much, everybody here, for listening to my talk, and especially to the organizers for the opportunity. It's a pleasure to be here. And of course, before I start talking about mathematics, I would like to share some of my something about my relationship with Cidinha, of course. And I was thinking, what should I say about it? No, there are so many things that I could mention. And then I made myself a question. I asked myself, what was the most important thing that I learned from Cidinha, and more than from anybody else? And the answer came to me very quickly. I think it's about how to see colleagues and students, especially, how to see their differences, their struggles, their difficulties, and their skills also beyond mathematics. Like this kind of holistic approach, to see everybody as persons, more than just mathematicians. And this is something that I've learned from her and that I carry with me. Try to bring this along my career on a daily basis. So yeah, that's what I wanted to share. And I am very thankful to her for all these important lessons that I had. So, well, talking about mathematics, I want to share with you today some new things that I've been thinking about. And the idea, let's say, the guiding question is, can one build a real analytic theory that keeps enough of rigidity of holomorphic functions to support singularity theory? So the thing that annoys me sometimes is that we try to work with real analytic singularities. That's something that I've been doing in the last years, and it's very difficult when you leave the complex setting. You lose a lot of the structure properties that you have in the complex setting. And it's strange because if you take a holomorphic function and you change the coordinates in a non-complex way, and topologically you have the same thing, if the change of coordinates is nice enough, of course. But it's not holomorphic anymore. So, and you still have all this topological Milnor fibration, the topology of the fiber, everything will be just like the complex setting because it's you have a diffeomorphism here. So the nature of the thing is not the holomorphicity itself, is something else. So what is this thing, that makes it possible to have all these nice structures on complex singularities? So I've been thinking about this, how to capture these and etc. So this is what I'm going to talk about today. So the main theorems of this talk is, so I'm going to define this set, this algebra P, which I'm calling perplex algebra. And then I'm going to define what a perplex function is. It's something analogous to a holomorphic function from Cn to C, for instance. And then we are going to see that this kind of functions has this Loyaczewicz, I'm sorry, I'm terrible with this pronunciation, but Loyaczewicz gradient inequality. And then we are going to see that they also have this very nice Milnor type fibration. So we have a good setting for the study of the topology of these kind of singularities. So this is the main results for this talk. Yeah, doesn't matter. So I start talking about the Milnor-Freiberger theorem because it's the final goal for this talk. So in the complex setting, we have this very well-known theorem. It says that if you have a complex function f from Cn to C, holomorphic, then for eta and eta and epsilon sufficiently small, you have this smooth locally trivial fibration, the restriction of f to the inverse image of a puncture disk, the eta, intersection a small ball going to the puncture disk, and this is a smooth locally trivial fibration. This is one of the pillar theorems in the study of topology of singularities. So the idea is to try to generalize this, but if you forget about the complex structure and just see this as a real analytic map from R to N to R2, the theorem, as it is stated, it doesn't hold. So you need something. Maybe you can have something not as rigid as the holomorphic structure, the complex structure, but you need something more than just the real analytic structure. So there should be something in between that gives you an analogous to this very nice structural theorem. So we are searching for this, no? So the problem is to identify a useful real analog of this rigidity. So before doing this, I want to give some other algebraic structure to R2, which allows us to have these nice theorems and structures. So before this, I need to mention, this is a very well-known result, a classic result, that, that says that any two-dimensional commutative associative algebra with identity over the real numbers is necessarily isomorphic to one of these three, either the complex numbers or the hyperbolic numbers, also known as split complex numbers, which is somehow can be seen as a direct sum of two copies of R, or the dual numbers. Okay, so these are all the three possible nice algebras in this sense. Okay, and I want to give to, in R2, I want to endow R2 with some nice structure, and these three examples should appear among these nice algebras, okay? Actually, n of them should be isomorphic to one of these three. So if you fix the complex structure, if you consider only this one, this is very rigid, but only one model. If you fix the real analytic structures, it's too flexible and too little control. It's not good enough in order to do this, to study the topology in a nice way as we do in the complex setting. So the perplex analysis that I'm proposing is something in between. It's the real two-dimensional algebras. It's not one, it's a family of two-dimensional algebras with a controlled Cauchy-Riemann type constraints. So that you can develop the theory in a way similar to the complex theory, complex analysis. Okay, so well, let's start doing this. No, stop talking and do the thing. So we start by choosing two triples of real numbers, A and B. So three real coordinates. Okay, and if I give you, or if you give me two A and B like this, I can define a product on R2 using these two triples of numbers. So the product is the following. I give you x and y, two vectors in R2, and we define x times y by this formula, let's say. So this is the definition of the product. So for instance, if you put here A equals 1, 0, minus 1, and B equals 0, 1, 0, you have the complex product, okay, precisely. If you put 1, 0, 1, and 0, 1, 0, you have the hyperbolic product, okay, the product in this, the second type of algebra, the split complex numbers. So, but you can take any other choices for A and B, right? So the product is automatically bilinear, commutative, and distributive. And the question is when it is associative and unitary, when you have an identity in the desired sense. Right? So the question, the answer is given by these equations and equalities and inequalities. So a pair AB defines a perplex algebra, meaning unital, associative, everything nice, if these conditions are satisfied. So you have two inequalities in R6, right? Because we are in R6, 6 real numbers. So you have these two inequalities and two equalities. If this holds, then everything nice, you have a nice algebra, which I'm calling perplex algebra. Okay, so you have a family of many possible choices. So these equations cut out a smooth four-dimensional semi-algebraic parameter space, P in R6. Right? And the identity, once you fix this nice pair of A and B, you have the nice algebra, perplex algebra, and the identity, and the identity is given by this, right? So you can. Okay, so examples, 3 examples. As I said, complex numbers, this is one case, one example of perplex algebra. Hyperbolic numbers, of course, is the next example. And dual numbers is also appears as a perplex algebra, as it should be. And of course, any perplex algebra should necessarily be isomorphic as algebras to one of these 3, because they are all the possibles, right? So, okay, so the thing is that in the first case, if you have a perplex algebra, which is isomorphic to the complex number, you have a field actually. But if you have a perplex algebra isomorphic to the hyperbolic numbers, then it is not a field anymore. You have non-zero divisors. Okay, so it's not a field anymore, but it's a nice algebra anyway. And in the case of perplex algebras isomorphic to the dual numbers, you have non-zero nilpotents. They appear. So for example, to this associated to this perplex algebra, to these pairs A and B, you have epsilon. You take this vector 0, 1 in R2. It is a nilpotent. The square of this under this product will be 0. Okay. So in order to be able to do anything interesting with this, we need to be able to identify the 0 divisors, for instance. So one way of doing this is to define, if I give you any fixed one perplex algebra, take an element there, an x, and look at this linear transformation from P to P. It's, well, this transformation. It's the left multiplication. So Lx of y is x times y, where this time is the product defined by that algebra, well, as we did before. Then we can define the perplex norm of this perplex number x as being the determinant of this matrix Lx. Okay, this is the perplex norm. It satisfies, I'm calling norm because it satisfies that the perplex norm of a product is the product of the norms, which is not obvious, but it happens. So it deserves to be treated as a norm. And we also can check, doing some calculation, easy calculation, that x is a unit, meaning invertible in this algebra, if and only if the norm, the perplex norm of this perplex number x is not 0. So it's an easy way of identifying the 0 divisors or of the perplex algebra. And then we can define z as being the cone of 0 divisors. So the perplex, non-zero perplex numbers whose perplex norm is 0. No? So the set of 0 divisor, and it is a cone. Okay. Okay, so actually it will be a union of 2 lines, always. Okay, so how to classify? I told you that a perplex algebra necessarily is isomorphic to one of those 3 classic examples. How to classify? Well, we define this discriminant delta given by this equation. Of course, everything depends on A and B, so A1, A2, A3, B1, B2, B3. And then you can form this discriminant by this formula. And the classification theorem is that if the discriminant is negative, then your perplex algebra is isomorphic to the complex numbers. If the discriminant is positive, then the perplex algebra is isomorphic to these hyperbolic numbers. And if your discriminant happens to be 0, then your perplex algebra is isomorphic to dual numbers. Okay, so this is the classification theorem, basically calculations to prove this. And then we can define a perplex algebra as being non-degenerate if you are not in this very ugly case where the discriminant is 0. So non-degenerate algebra means the case when the discriminant is not 0. Okay, so you don't have these non-zero nilpotent elements. Okay, but not necessarily it is a field. It can have 0 divisors. Okay, so I want you, in order to be able to do something interesting, first we need to develop some kind of differential calculus for this. So I'll try to do it quickly, okay? We need to define what it means for a function to be differentiable in this perplex sense, okay? So in order to do this, I first need to study the direction of 0 divisor because it plays an important role. I'm going to tell you why. So we define this Z in the projective space, the real projective space, as the set of 0 divisors directions, okay? And you have 2 directions of 0 divisors. And we say that a sequence UK of units in your perplex algebra going to 0 is positively separated from Z if it doesn't convert to these problematic directions, these 0 divisor directions. So in other words, if after normalization there is a constant C positive such that the perplex norm in absolute value of the sequence is always bigger or equal than this constant C. So it's not going to 0 though. Okay. So this is what we mean by, it's very technical, but boring, but it's we need this definition. Okay. So positively separated from the problematic directions, the 0 divisor directions. And then it's nice, but we need this because if a sequence is positively separated from Z, then there is some constant M, positive constant M, such that the product of the real norms of UK times the inverse of UK is smaller or equal than M. Of course, if you are in the complex set, in the complex algebra, for instance, the product of the norm of one complex number and the inverse is 1. So it is limited. But if you go to some other arbitrary perplex algebra, this is not the case. The product, you can have a sequence of perplex numbers going to 0, such that when you multiply each element of the sequence by the inverse, this blows to the infinity. Okay, but not if you are away from the 0 divisors directions. Okay, so this is necessary in order to be able to define the differentiability, which is what we do now, finally. So now I give you one perplex algebra and one function f from P to P. So you can see this as a function from as a mapping from R2 to R2, but with this perplex algebra fixed. We say that this function is P differentiable at X if there exists some perplex number L. It's very analogous, of course, to the definition of holomorphic function. If there exists some perplex number L, such that for every positively separated sequence HK of units going to 0, this limit equals L. So it's the usual definition of the derivative, but changing the product, of course. So this is the product. Instead of dividing by H, you multiply by the inverse of H. And of course, by multiplying, I mean this is special multiplication defined by the algebra. And when I say the inverse of K, is the inverse in this perplex sense, of course. So that's the definition of the derivative. We write L equals f prime of x, is usual. And it's very nice because once you set this definition, the usual rules for derivatives, they hold. So the derivative of the sum is the sum of the derivative of a product of 2 functions, the derivative of the first times the second plus the... So all the usual rules that you... Sorry? No, not the chain rule. That's why it's not written there. Then it's more complicated. Yeah. You asked precisely what I cannot answer. So that's why it's missing there. It's not that I forgot about it. But this other simpler property they hold, right? And very nice that polynomial functions over this perplex algebra, they also have the expected form of the, so the derivative of x squared is 2 times x. The derivative of x to the third power, but now when I say x to the third power, it means x multiplied by x under this product, of course, no? 3 times. The derivative of this would be 3 times x squared in this perplex sense. So you can derivate polynomial functions in the same way you do for complex functions. Otherwise, it will be very difficult to work with, right? But yeah, everything works nicely with this definition. And what is more interesting is the Cauchy-Riemann equations that we can bring to this setting. So if I give a perplex function f from P to P, you can see it in real coordinates, u and v. So u and v are functions from R2 to R. If it is P differentiable, we can show that the derivative can be written as you take this vector 1, 0, is the identity in the complex setting, but for a general perplex algebra, this is not the identity anymore. It's just one perplex number. But you take the inverse of this perplex number in the perplex setting, multiply by this vector. These are the partial derivatives of u and v in the real sense. And this gives you the derivative. But this is, we can show that this is also can be written as this product. So there is an equality there. And this is what we call the generalized Cauchy-Riemann equation. This equality. So you have this equation. So this is our Cauchy-Riemann. If you put here A equals 1, 0 minus 1, B equals 0, 1, 0, so you are in the complex setting, this gives you precisely the usual Cauchy-Riemann equations. Okay? But it works for any perplex algebra. Okay, so in the complex case, so you have the usual Cauchy-Riemann equations, and in the hyperbolic case, you have these equations. Okay, just as examples. Right? So everything works very nice, just like in the law, which is very nice, just like in the complex setting. And the theorem, well, why do we care about the Cauchy-Riemann equations, right? Well, it's because of this theorem. If you have f from R2 to R2, a mapping of class C1, and AB defines a perplex algebra, then f is P differentiable, so differentiable with respect to this perplex algebra, if and only if it satisfies the generalized Cauchy-Riemann equations, as it should be, of course. So it works, and this is how you can check. So if you give me one function from one mapping from R2 to R2, if it is holomorphic, perfectly, you already know how to do everything. But if it is not holomorphic, maybe it is p-holomorphic or perplex for some good choice of pairs A and B. So that's, and then if this happens, what I'm telling you today is that you can do a lot of things analogous to what you do in the complex setting. Well, yeah, the proof, I don't have time. Yes. So what about critical points, right? So now we can talk about a differentiable function from P to P. Well, for a p-differentiable map or function from P to P, one has that x is a critical point of f in the real sense, as a mapping from R2 to R2, if and only if f prime of x, so the perplex derivative, it doesn't have to be 0. It has to be a non-unit. So, of course, in the complex setting, this means being 0, because 0 is the only non-unit. It's a field, right? But here's more general. So this is how we characterize the critical points in this setting. Right? So in the hyperbolic case, non-zero divisors can also give critical points because because of this result. And this is one of the first places where the perplex and complex theories separate, because you have these other kind of critical points, right? So well, so now the question is, how frequent are these perplex maps? So I told you, if you give me one a real mapping from R2 to R2, If it is complex perfect, you already know how to do everything. If it is not, maybe it is perplex for some good choices of A and B. So how frequent does this happen? That's the question. No? So it would be very nice if you could, if the set of perplex functions, so I'm calling a function from R2 to R2 perplex, if it is P differentiable for some good choice of P, for some perplex algebra, right? So that you can do everything you want. It would be very nice if the set of all perplex functions were dense in the set of all mappings from R2 to R2. This is not the case. It's a big set, of course, but not dense, not that big. But for instance, if you look at quadratic perplex functions, they are dense among quadratic real polynomial maps in the Whitney topology. So at least for this particular case, you have a huge, dense set. So it's worth investigating this. So we can prove this. I'm not telling you today because there's no time, but we can prove this. Okay, so this is just like functions on one variable. It's kind of boring. So of course, we would like to talk about functions on several perplex variables. That's the next step. So you can define Pn in the usual way. So a point P with these coordinates Pi, perplex numbers for some perplex algebra fixed. You can endow it with the module structure component wise. So X and P is this an uple P1 Pn, and X is any perplex number. The product will be coordinate wise, right? As it should be. So it defines a module over P, analogous to Cn, of course. And then we can look at functions f from Pn to P, right? And then we can define partial derivatives in the natural way. So you define a canonical basis for Pn. So you have the EIs, the canonical vector, the canonical base. EI, so for instance, E1, it will be the vector. Well, not the vector, but 1 on the first entry, but this one is not the number 1. This one is the identity in this perplex algebra. So the identity is 0, 0, 0, 0, and so on. No? So this way you can define the partial derivatives in the most natural way. I'm sorry, I'm going very fast, but it's I want to say a lot of things. But so you can define this where the limit is taken along units separated from zero divisor, as I told you in the beginning, and then you can define the analogous, let's say, gradient. I would say gradient vector, but it's a model. But you have this this gradient for the function f defined in the natural way, right? So we can mimic the complex setting. And then we can define this directional derivative. So basic course on differential calculus. No? Then you have the differential derivatives. And then comes the good thing that if you have f from R2n to R2, so you can see you have a f from Pn to P. And you can also see it as a function from R to N to R2, right? So when you look at in the real setting, you have the differential, so this dfp, the capital F. If you look at it in the perplex way, you have this small dfp. So the perplex derivative, the real derivative, and they coincide, as it happens in the complex setting, right? Okay, and thanks to this, we can define a critical point or a regular point, because a critical point in the perplex sense will be a critical point in the real analytic sense, right? So it's very easy to detect this way, these regular or critical points. And if you have P a regular point, then the kernel of dfp is the kernel of the differential in the real sense, which is, of course, the tangent of the fiber containing the point, right? And this fiber, this tangent, TP of the fiber containing the point, it has a perplex structure. So it is a perplex hyperplane. Just like in the complex sense, you have the tangent. It's a complex hyperplane. So here is a perplex hyperplane. Why do we mean by this? The natural definition. It's a free P module of rank n-1 in Pn. Okay, so I have this analogous structure. So far we basically have everything we want, everything we need, everything that happens in the complex sense. But we are talking about a much more general situation here. And then we can finally define what a map or function from Pn to P is, what it means to say that it is P-analytic. We say that this function is P-analytic if it is P-differentiable and its real coordinate functions are real analytic. So we are mixing things here a little bit. So this definition is deliberately hybrid. And this real analyticity, it will be important because it supplies the analytic estimates needed for stratification and fibration, which are our final goals by the end of the day, right? So this is the definition of a P-analytic function, perplex function. And the theorem, this Loyaczewicz gradient inequality, is the following. If f from Pn to P is P-analytic with f of 0 equals 0, then there exists a neighborhood U of 0, a constant, positive constant C, and theta between 0 and 1, such that this is the real, the usual real norm. Well, the maximum norm, but it doesn't matter a lot. But, well, you have this inequality. It's the same, the analogous to the usual Loyaczewicz inequality. And this inequality gives a lot of things, right? A lot of theorems that we have in the complex setting come from this inequality. So this is telling us that, okay, so this seems to be a fruitful setting. There is hope that we can do interesting things there. Thanks to this. I'm not going to show you the proof of this inequality. I can tell you the idea behind it. So you write F equals U of V, and thanks to the generalized Cauchy-Riemann equations, it implies that the perplex gradient controls the real gradients. So you have this inequality. So you can go to the real Loyaczewicz inequality and do everything there. That's thanks to the generalized Cauchy-Riemann equation. So we apply the classical real inequality to U and V to get this. And after shrinking the neighborhood and choosing a common exponent, we have the desired inequality. Okay, so for you to see that. So we do have this inequality. That's this was our first main theorem. Okay, and then we can do things. We want to do things with this. That's towards singularity theory and towards the study of the topology of these perplex functions. Okay, one corollary of the inequality is that if f from R2n to R2 is perplex analytic, with so P differentiable for some perplex algebra P, and f of 0 is 0, then near the origin, every point outside the f minus 1 of 0 satisfies this. The differentiable, either you see it as the real derivative or the perplex one, they're the same. It is not 0. So when we form the matrix, it is not 0, 0 everywhere. Right? In the complex case, non-critical typically means rank 2, of course, but not now, not in the general perplex algebra. Then, in the perplex case, rank 1 can occur. It does happen in the hyperbolic setting. And this reflects the possible presence of non-zero divisors among partial derivatives. Okay, but we do have this. And then, well, we want to develop tools so that we can study the topology of these perplex functions. And well, at least for me, like the first one I learned, and the one I like the most is the Mueller-Le type fibrations. For me, it's like a starting point. So I wanted to have this kind of Mueller fibration for these perplex functions. And then when I go and say, oh, okay, how do they prove this in the complex setting? And then I found this very nice proof due to Ham and Le. And it relies basically on the fact that these complex functions, they satisfy the Loyachevsk's inequality. And I also have the inequality here in this case, so it should work, and it does. So it's basically adapting their proof, and everything works fine. So in order to tell you the story, I need to first start with the definition of a good stratification. So following Ham and Le, we do the following. So I give you a function f from Pn to P, and I look at V, the zero set of this function, f minus 1 of 0, in R to N. And I take as a witness stratification of this real analytic set V, right? Okay, we say that this stratification S is good at 0 if whenever you take a sequence of points in U minus V going to V, so U is the neighborhood, V is the zero set, you take a sequence outside V going towards V, and look at the tangent space of the fibers which contains these points, Qi. So we have a sequence of points Qi's. For each point, there's one fiber containing the point. At that point, there's a tangent space. So we have a sequence of tangent spaces. And if this sequence of tangent spaces converge to some plane T, one has that this T contains the tangent at this point Q, the limit point Q, on the stratum that contains the point. So this is what they call the good stratification. It has nothing to do with this perplex thing. It works for it it just uses the real analytic structure, right? And good stratifications, according to them, is the bridge from analytic estimates, the Loyachevsk's inequality, and local topology. So I'm going to use this bridge. Okay, so the theorem is analogous to Ham-Le's theorem. Let P be a degenerate perplex algebra. Then every P analytic function from Pn to P admits a good stratification, just like in the complex setting. So it works in the field case, of course, and also in the non-field case, which is amazing. Well, here I say non-degenerated because it's not that it doesn't work in the case of the algebras, the perplex algebras, which are isomorphic to the dual numbers. Maybe it works, it's just that I don't know, at least yet. So just to be safe, we exclude that case. It admits a good stratification. And the proof follows Ham-Le strategy. You just go adapting to the perplex setting and using all this, a lot of inequalities that we can develop. So it's a little bit technical, so I'm not doing here, but we can prove this. Following their steps also, it's not following their steps. So this is, I don't have time to, I'm going to skip this. So we can prove that they have this. So then we can finally talk about Mueller-Le type fibration, because if you go to the complex setting, if I give f from Cn to C, how do you prove that they admit a Mueller-Le fibration? You basically use the fact that they admit this good stratification, or if you want to call this Thom AF condition, it's all those different names. I don't know why, so many names. I get so confused, so I just picked one. So everything relies on this fact. No? So you basically want to use Ehresmann's fibration theorem, and in order to do this, you need to have like a transversality of nearby fibers with small spheres. And you get this from the Thom AF condition or from the existence of a good stratification. And we do have a good stratification in this perplex set, so we have all the tools we need. And then we have the theorem. So first let this delta f be the image of the critical set of f. So I give you f from Pn to P. It has its critical points, and you can look at the image of these critical points, which usually we call the discriminant set of f. That's our delta f. And the theorem is, if P is a non-degenerate perplex algebra, and f is a perplex function from Pn to P, in this sense, P analytic taking 0 to 0, then there exists eta and epsilon sufficiently small such that the restriction of f to this setting, so this is, let's say, the Mueller tube, excluding the discriminant, of course, intersection with the ball going to the disk minus this discriminant, it is a smooth locally trivial fibration. So you have this pillar theorem of the complex singularities working here also. So you can generalize. So this is the main theorem. Good stratification gives transversality with small spheres, as I told you, and Erisman's theorem gives the fibration. So this is just something that I've been doing recently. I'm pretty sure that much more can be done, because so the idea is just to consider everything you know how to do, all the problems you know how to solve in the complex setting, and asking yourself why to stay only in the complex setting. If maybe you can do in more general settings, because you have a lot of things. So holomorphicity is not everything. So there's something deeper there that maybe you don't have the holomorph, but you still have good things happening there that allows you to do more things. So it's something in between the very rigid complex setting and the very wide real analytic general setting. No? So what this theorem that I'm proposing gives? It gives a 4-parameter family of, because you have a lot of perplex algebras. Why it is you have a 4-parameter family of real 2-dimensional algebras unifying the 3 classic 2-dimensional algebras: complex numbers, hyperbolic numbers, and dual numbers. An analytic structure governed by the generalized Cauchy-Riemann equation, a calculus compatible with polynomial functions and several variables, a Loyachevich's gradient inequality for perplex analytic functions, and a Mueller-Ley fibration theorem for non-degenerate perplex algebras. This is what I can do so far, but I'm sure that we can do much more than this. So open directions that, well, I think there are many open there, but just to list some of them. So first one could and should ask, what about the topology of the Mueller fibers? Okay, of course, if your perplex algebra is isomorphic to C, then the Mueller fiber that you have now, it will be diffeomorphic to the complex one, of course. But what about the hyperbolic case? No, what can happen there? So it will be a product, a Cartesian product, because you have the split, as the name says, split number. It splits as a product. So so it's interesting already in this sense, but you can try to say more because you have tools now to do this. So what about the topology of the Mueller fibers, and how do they change? Because you have the discriminant splitting here, the disk, so you can ask yourself how the topology changes, and it's easier to do this in this setting since you have more tools as trying to do this in a general real analytic function, of course. You can ask yourself also about the perplex analogs of Lie numbers and polar invariants, because you can define these things here also. Classification of perplex singularities under right-left equivalence. Stratification theory, in this case, regarding this perplex structure. Geometry of analytic sets defined by p-analytic equations. And also dynamics of iterated perplex analytic maps. So these are just to list a few of the directions that could be explored. And yes, thank you very much. And questions and comments are welcome. Thank you.
Thank you very much, Aurelio. Are there any questions or comments?
Okay, so I have a question about the discriminant in the mean or left vibration. So in the holomorphic case, this is just the origin, no? But in the general case, can you say something about this set? Is it analytic? Is it dimension 1 or?
It has dimension 1. Well, it depends, because it can be also just 0 if your perplex algebra is isomorphic. But if your perplex algebra is isomorphic to the hyperbolic numbers, then it will not be, for sure, not be just 0. Because you have a lot of critical points, because
no, you have analytic, or do you have some structure? Or
no, not linear in general, no.
Analytic.
Analytic, I don't know. I don't know, but I don't think so. Subanalytic, yes, right? Because it's given by the equations. But I don't know. Didn't think about it, but I don't know.
Thank you.
Good point.
Hello, Aurelio. Thanks. Nice talk. Now I understand why you call it this the perplex algebra, because much properties will become perplexed, as you see. I think that's the motivation. I don't know, but
actually, they at some point these hyperbolic numbers at some point they were called perplex numbers. I didn't know this. First, I named this perplex because I was perplexed. But then I found out that someone used, but it's not used anymore.
So. But my question is about the chain rule, because I think that if you, I don't know if you have already determined conditions in which the chain rule holds, but I think if the chain rule holds, then you can avoid the real analyticity in each component. So because you can maybe develop a manifold theory and something like that. Have you think about this? So
no, I didn't. And about the chain rule, to be honest, I don't know if it, because first I did some calculation. I kind of found some examples where it failed. I didn't manage to understand why, but then I stopped doing that, and maybe it does hold. I don't know if it holds or not, to be honest. This is very raw. I just started doing this thing. It's very raw. I don't know.
Yeah.
But it's a good question. And the answer is, I don't know again.
Very well. Maybe let's try to investigate this together, because I'm very excited to know these perplex numbers.
Yeah, sure, cool.
Okay, thank you.
Thank you.
Are there other questions or comments?
Thank you for it. Oh, sorry. Can I?
Yeah.
Yeah. Thank you for the talk. So how much big the set of all perplex functions in the whole of
if we are talking about one variable, more than one variable, I have no idea. I didn't think about it. I thought about the one variable case. Then in general, it's not dense, as I told you. If you restrict to quadratic maps, then it is dense. More than this, it is not dense. I know that it is not dense. How big it is, I don't know. I don't know, not even how to try to. I don't know how to measure. I don't know. Again, I don't know.
Cannot we estimate some codimension of the
maybe. I did maybe, but as I said, it's very raw. I don't know. I didn't try and I didn't think about it. Okay. But it probably would be interesting to. I just my first I was, because I was hoping it would be dense, so I was so excited about it, and then I saw it was not. Then I okay, let's do something else. But yeah, it would be nice to understand how big it is. Yeah.
Yeah. Thank you very much.
For the perplex numbers, analogous of the doubling procedure for complex numbers. You double complex, it becomes quaternion.
No, I thought about the building the tower. You know that they do these towers of complexes. So you take C times C, and I thought about this. I started writing something about, but not in the sense. No, Didn't think about it, no. Sorry, I don't know anything. I told you everything I know, basically.
You mentioned the geometry of the fibers. Is there a chance one can define something like curvature or place where this is not flat in some sense?
Sorry, again, I don't know. I don't know. Probably, no, probably.
And the reason I ask this question is because of the study of these Milner fibers, where you can prove that, in fact, the curvature is concentrated on very small zones when you go to the limit. And then I was wondering if something can be just concentrated on small places on your fibers, close to the origin, and the rest is in some sense flat.
Yeah, I don't know. I didn't think about this because usually I don't think a lot in geometric terms, but I did think about the vanishing cycles, which are also there considered. So it's the topological version, right? So I thought about it, and but I don't want to claim anything yet, but I'm pretty confident that it works in an analogous way, because it doesn't rely again on the rigidity of holomorphicity so I would guess yes, but I cannot claim anything.
Thank you.
Thank you for the question.
Thank you very much, Aurelio. And let's thank the speaker again.
Thank you very much.
Now the organizer. So it's a great pleasure to introduce my friend, collaborator, and academic daughter, Ellen Santana from SCAR. Thank you, Ellen.
Thank you, Nivaldo. Hi, everyone. I'm very glad to be here to speak in the workshop. It's always an honor and a pleasure. Thank you very much. I want to recognize all the effort and energy that the organizing committee has put together to make this conference possible. In special, of course, Miriam and Thais. Thank you very much for all the energy and all patience that you have to make this possible, to make this international workshop in honor of Cidinha. In honor of Cidinha. Unfortunately, I cannot say that we were friends, and I do not have beautiful pictures, personal and family pictures, as we saw in the talk of Alexandre and Isabel. That is true. But I wanted to share with you all the impacts that Cidinha had in my life, in my personal and professional life, even though we were not intimate. So for context, I finished my PhD in the end of 2019. And in 2020, I was a volunteer postdoc here in the Institute with Nivaldo. And in that year, me, Nivaldo, and Amanda, which was another PhD student of his, maybe this is turn, I don't know, it's fine, my microphone, right? Yeah. So we were organizing the seminars of singularity theory, which was, I mean, it was in person here, but during 2020 it was online, right? And at the end of the year, in December 2020, she sent this email to us, to the three of us, recognizing our work, which is such something that Cidinha would do. I mean, she had a lot of things to do, but she found the time to recognize every little effort that someone has in the group. So I wanted to share that with you. After more than 1 year without funding, I decided to go out of the academia, work out of the academia for obvious reasons. And I was not really doing math in 2021. But I was invited for a lecture and an online lecture. And after, she was in the audience, and she sent me this email saying that she liked my enthusiasm, and she was glad that Nicola was there to watch it. Where is Nicola? Nicola Duterte was also my advisor during my PhD. And she was asking here if I was applying for some position, which I was, but I was not getting it. But she was hoping and wishing that I could succeed at some point. But at that moment, I was sure that I would not go back to academia because things were not that very easy, job-wise, I would say. And then in April 2022, I received this email of her, for me, and a dear friend, Rafaela. Many of you, I'm sure, know Rafaela. It's not Rafaela from Nivaldo, it's another Rafaela, but in the Rafaela from Tomazella, actually. So we got this email of her saying that we should apply for a postdoc with her. And I was thinking, okay, I will not get it. It's been more than almost 2 years. It's not possible. I will not get this position, of course. But for all of us who knew Cidinha, there is no answer. When she asked or suggests something, we simply, I mean, this is my perspective, we simply do it, right? And then I did it, and actually I got the position. And this is how I went back to academia. And after that, I applied for a position in the university, and this is how I am here. So what I mean is that I really like what Aurelio told us in his lecture. He was asking which was the main thing that he learned from Cidinha. And for me, I want to answer that now, is that we can encourage people with our words. Maybe this is what we need to do. Maybe we should use our words to encourage people who work with us or our students. So I think this is what she taught me. Okay. She mentioned to me, I would, maybe I mixed up some things here. I will go back just to tell you this. I will speak about the auto obstruction of determinantal singularities. And I wanted to just mention how this is also in honor of her, because in the end of my PhD, she invited me to her office, and she explained to me some things about determinantal singularities, which I could not follow. I didn't follow that path because I had other things to do, other ideas with Nivaldo and Camila. So we pursued that path. And that is something. And this position that I applied and I got, this postdoc that I applied, that I showed you the message, I was very lucky because at the same point, Barbara, which gave us a lecture this morning, she was also a postdoc here. And we worked together and we could produce a paper which was published before Cidinha passed, which is very, this is something, a reason of joy for me. But she proposed to me and Barbara, right, Barbara, that we look at our paper, our results, in this context of determinantal singularities. And we could have done so far, but we will, right, Barbara? We will. But the thing is that actually I worked on determinantal singularities in another idea, and this is what I wanted to show you, okay? So let's go to math, and now I will describe to you the universe of determinantal singularities, and I will be specific when I have results of my own. This is a joint work with Anna Frubs-Kruger from Algebraic University. So here I'm following the work of Ebeli and Guzenzade from 2009, and okay, we take then the space of matrix of who has rank less than T in the space of n by n matrices with complex entries. And we say that this is a generic determinantal variety of this type when this is what we have. So the set of matrices n by n with complex entries and rank less than T. This is a singular variety, which is called generic determinantal variety. It has this codimension in this space. And a very interesting property of this variety is that the singular set of this variety is also a generic determinantal variety. But is given by the set of matrices with rank less than T minus 1. This is it, okay? And also, just for, this is a good observation, is that this variety has a Whitney stratification given by the rank, right? Giving like this. So when we look at this set, see, when we are taking a set of matrices with rank less than I, and we are removing the set of matrices with rank less than I minus 1. So this is smooth, and this is the, I don't know what I'm doing wrong. There is a sound, right? But it's fine for you. You can hear me, right? Okay. So this is a complex stratification, Whitney stratification. So a determinantal singularity will be the following. We will take a holomorphic map germ, F, from Cn to the space of matrices, M by N matrices, and we will look at the inverse image of the generic determinantal variety by this holomorphic map, okay? This is a determinantal singularity in the case where this variety has the expected codimension, the same codimension as the generic determinantal one, right? Okay, this determinantal singularity would be called, this is from Ebeli and Guzenzade, essentially isolated determinant of singularity if the map F, that map that defines our variety, is transverse to the rank stratification. So that Whitney stratification that we saw over here, so that map will be transverse to each stratum of this stratification, all right? So in that case, in a punctured neighborhood of the origin. So at the origin, we can have non-transversality, okay? But out of that, this is what we have. So in that case, Evelyn Guzenzade called this germ essentially isolated determinant of singularity, EIDS, okay? For example, so here we have a map from C4 to the space of 2 by 3 matrices, giving like this, right? So when we look at the inverse image of the matrices when we make the 2 by 2 minors, when we make the 2 by 2 vanishes, the 2 by 2 minors of these matrices, we obtain this variety, right? So here we are just doing the 2 by 2 minors. So we have this variety, which is a surface, which means that it has codimension 2 in C4, and then this is an EIDS of this type. So we are looking at the 2 by 3. We have a matrix of 2 by 3, and we are looking at the T, the rank that we are vanishing is T2, okay? All right. Another notion that will be important to us is the notion of essential smoothing. So it is true that there are contexts, for example, isolated complete intersection singularities, where we can deform a bit our variety and obtain a smoothing, right? We make the variety smooth. This is not always the case when we have a determinant of singularity. And this is why Evelyn Guzenzade present this essential smoothing, okay? This is what we are understanding now. So an essential smoothing of a determinant of an EIDS actually will be an stabilization of the map F that defines our function, that defines our variety, all right? So what is the meaning of that? So we have giving F, the defining map of our determinant of variety, F2 will be an stabilization in this sense. So when we look, we have X to be an element in Cn, which is our ambient space. And we have a space of parameters that I'm denoting here by U. And when U is 0, we have the map itself, the map that defines the variety itself. And when we have U different from 0, sufficiently small, we have this map transversal to M, to the generic determinant of variety. Okay, so in this case, I'm not sure if it's clear, but in this case, our X is given by the inverse image of F by MT, by this generic determinant of variety. And this is what I mean by an essential smoothing. In general, it has to be a microphone hidden somewhere, but we are not going to pay attention to that. Okay. Let's see an example. Okay, I remember. Okay. What I wanted to say is that here the definition, the formal definition says that the essential smoothing is the stabilization. So it's a family, right? But for me, in this lecture, we are calling the essential smoothing a representative of that family. Okay, we are choosing one U, and that would be the variety given by that F tilde U will be our essential smoothing. I will explain in the example, okay? So giving this variety, this determinant of variety, here I didn't read it, it's not written, but X, our EIDS, is the inverse image of the 2 by 2 minors, is the vanishing of the 2 by 2 minors of this matrix, okay? So an essential smoothing would be, by the formal definition, this family, right? So here we have F tilde U. You are believing in me that F tilde U is always transversal to the generic determinant of variety that we are using it. Here T would be 2, actually. I put T, but it's 2 here. We are in the case T equals 2. So this FU, if F tilde U, is transversal to this space. All right. And see, when we make U equals 0, we are back to the map that defined our variety initially, okay? So this is for, by the definition we saw before. But in general, I will always take the essential smoothing to be the variety given by a member of that family, okay? So here, I did not take any u, I put it u equals 1 to the 100. And for me, the essential smoothing will be the variety given like this. So the inverse image of the vanishing of this 2 by 2 determinants, okay? All right. Let me see. Okay. The thing is, why do we have 2 examples? Because I just saw it here that here I put 10,000 and here 100, but don't pay attention to that, okay? Maybe nobody saw it, just me, and now everybody sees it. But in any case, what I mean is why I put it 2, because there are cases in determinant singularities where when we look at the x tilde like this, our essential smoothing, this is actually a smoothing. This is possible, okay? We make the deformation and it's true, we get a smooth variety. But this is not always the case, okay? So, for example, if we take this fourfold, so we are taking from x1 to x6, we are looking at this 2 by 3 matrix. An essential smoothing, so a member of that family, will be something like this. Look what we have over here. This is x here is given by the inverse image of M2 to 3. This means that we vanish all the 2 by 2 minors, right? So how do we find the singular set of this variety? We look at the 1 by 1 minors. We vanish the 1 by 1 minors. Vanishing the 1 by 1 minors means that we are vanishing x1. 1 by 1 minors would be the entries, right? So we vanish x1, 2, 3, 4, 5, and also this element here. But if x1 and x2 is 0, also x6 is 0. So this variety has isolated singularity, right? But if we look at the essential smoothing that I'm giving you, think again. The essential smoothing is again an EIDS. And then to find the singular set of this variety will be vanish the 1 by 1 minors again. So we vanish here all the entries, x1, 2, 3, 4, and 5. And when we are vanishing this entry, we have 2 possible values for x6, right? So we have 2 points. So we started with a singularity, determinant of singularity, with an isolated determinant of singularity. And when we make this essential smoothing, we obtain 2 singularities, right? This is the phenomenon that is not possible here, okay? All right. So the title of my talk is I wanted to present you a formula for the Euler obstruction for determinant of singularity. So what I did so far was to introduce determinant of singularity and show you what can happen in this setting, okay? Now I want to present the definition of the local Euler obstruction of a one differential form, okay? So now we will construct here a diagram that I do for, ever since I finished my PhD, is the same diagram. But we have news today, which is pretty exciting. I will show you in a moment. Well, exciting, at least for me, right? So here I will put our EIDS, our determinant of singularity, and I will consider the Nash modification of this variety. This is a huge deal for me, because for several years I denoted like this, but now this is this essential smoothing. And so do not be mad for me to put the bar. There's the reason there's no enough symbols for me now. So this would be the Nash blow up, okay? All right, and associated here we have the Nash bundle, okay? So this X here, this construction that I'm doing now, it works for complex analytic varieties, okay? Right. So here, I would just put it, mention that this variety is included in Cn. And what is happening is that we can consider a one differential form in Cn. Let's call this inclusion here J, and this map here nu, as usual. At least one thing as usual. So we can consider the pullback of this one form to the Nash blow up, right? And yes, and then we can consider an epsilon is small enough for it. This pullback is non-zero, is a non-zero session of the dual Nash bundle. Let's just put a star here. So so it's non-zero, as a non-zero session of the dual Nash bundle in the inverse image of the sphere. In the inverse image of the sphere. All right, let's see. So this would be my omega bar here. Okay. And then we denote it like this, the obstruction cocycle for extending omega bar, this pullback, from the inverse image of the sphere into the interior of the ball, right? And this will be the denotation for the fundamental class, the corresponding fundamental class, and then we can make the evaluation from this class to this to obtain an integer. We are working over integers, right? This is the Euler obstruction of the one differential form omega. Okay? In the case, and this is for Danielle Duarte, in the case we have the differential of the square function, instead of any omega, we obtain the local Euler obstruction, right? So in this case, the Euler obstruction of omega will be the local Euler obstruction. Okay, and this is for Barbara. When we have the exact forms, right, Barbara? When we have df, then the Euler obstruction of df, I will put omega, but omega equals df here, up to the signal of, depending on the dimension of the variety, we have the Euler obstruction of a function. This morning, I mentioned Barbara several times, but this morning, who attended her lecture, she computed several algebraic, she presented algebraic formulas and several invariants for, in this case, right, when we have one differential forms and also when we have the differential of a function. So there is, I'm sure there is a lot of connections that is possible to make also in this context. It's just a comment. All right, so this is what we have. So this is the Euler obstruction of a one differential form. And the exciting news that I told you. So this is always what I do in any lecture I gave, but we can continue this diagram when we have an EIDS. This is for any complex analytic variety, but when we have an EIDS, this is what happens. We can put here the generic determinant of variety, which defines X. Here is the map that we use. We can also use the same generic determinant of variety to take the stabilization. Remember, the essential is smoothing. So with this, we define X tilde, the essential is smoothing, which is also in the same ambient space. I will put J over here also. And this is what we can do. We can consider the Nash blow up of this variety. This is a complex variety. We can consider its Nash blow up, which in this case is also a resolution. It's not always the case, but for generic determinant of varieties, it is. And then we can make the product, so this product between X tilde and the Nash blow up, or the resolution of the generic determinant of variety. I put it in the other way because this is how Algebraic do, and yes. So it's the fiber product, so it's over empty Mn here, okay? All right, so here we have arrows also. But the thing about this fiber product, and this is in Ibli and Guzezadi work, the thing about this is that there are two natures. This is a resolution of X tilde, and it is a Nash blow-up of X tilde also. So here we can also define, we can also consider the Nash bundle in this setting. Okay? So the omega that we started here, the one differential form that we take in Cn, okay, let's put a P, capital P here, small p here that I'm not going to use right now, but this procedure of taking the pullback over here, we can do it in this side. So we can take the pullback of omega over here. So what do we have here? J composed to capital P. We have this. And again, we can take an epsilon is small enough for which this one differential form. Do I have a notation for that? Yes, I do. This one differential form is a non-zero section in the inverse image of the small sphere again. So we can use obstruction theory again here. So we denote like this omega hat to be this this pullback, sorry. And then we can look at the obstruction to extend this non-zero section of the dual Nash bundle from the inverse image of the sphere to its interior again, right? So we can evaluate, I didn't put it here, but that evaluation that I showed you, so we can again evaluate to the corresponding fundamental class, obtain an integer, and that would be the Poincare-Hopf-Nash index of X, the EIDS, the Poincare-Hopf-Nash index of omega over the EIDS X. Yes, okay. All right, so here is pretty much the, I would say, same construction that we had, but we are looking at the essential smoothing, right? This is our variety. And a good thing here, and this is provided also by Evelyn and Guzenzade, is that we have a geometric characterization for the Poincare-Hopf-Nash index. So they prove that it is the number, let's read together. So it is the number of non-degenerated singular points of a generic deformation of omega tilde over the non-singular part of the essential smoothing. So it's the number of critical points. So this is a sigma to denote the critical points. So the weird sound is gone now. So omega tilde in the regular part of the essential smoothing. I will put it here so when we make an example, we remember what we are talking about. Here we see that we are looking at, it's not omega itself, it's omega tilde, a generic deformation. This means that we are looking at things like that. Omega plus a small t, L, let's put here, where L is generic, a generic linear form. As usual, okay? All right. So let's see an example. And here is my first contribution, an explicit example of that, okay? So we consider this IDS, we already understood it, right? How to see that this is has an isolated singularity. We are vanishing the 1 by 1 minors here, so we find it only the origin as a singularity. And we are considering this essential smoothing. See that instead of 1 to the 100 or 1 to the 10,000, I took a very small u. It's a sufficiently small u, okay? And I say here that from the determinantal structure of X tilde, we have 2 points, but we understood it together. We vanish all 1 by 1 minors again. So we find these 2 elements. I chose wisely so I can find it at the coordinates, right? Okay. And then I will consider these 2 one differential forms. So we have here omega, and we have here a linear form, a generic linear one. I put it both of them because to compute the Poincare-Hopf-Nash index, of omega or in the EIDS, we need to work with a generic deformation. So I need our omega and a linear one that works, a generic one, right? And this one works. So how do we find this number? How to compute this number? Let me see the time. Okay, it's fine. How do we find this number? We need to find the count. We need to count the critical or the zeros of omega tilde over this variety, the regular part of the essential smoothing. How do we do that? Well, we will look at critical space, how to define a critical space. So we are, in that example, let's go back so I don't fool you. See, we have the fourfold because I obviously took one that I know the dimension, but we have a fourfold in C6. So to find the critical space of this restriction, we need to build a Jacobian matrix, right? And look at the right size of minors. The right size is n minus d plus 1, right? So n is the ambient space, d is the dimension of the variety, and this is what we need to see. So it's 6 minus 4 plus 1. So we need to look at the 3 by 3 minors of this matrix. So here we have the Jacobian, the 3 first line, we have the Jacobian matrix of the defining for the variety, right? The defining equation of the variety, x tilde. And we augmented with this line that has the coefficients of our generic deformation, the coefficients of this one differential form. This is what we are looking at. If you paid attention in lecture about forms that we had in the morning, this for ICES would be the GSV index, right? It's the same way that we computed. Okay, but let's continue what we are doing. So this is it, okay? You would be very horrible here, so I put it like this, okay? And so we need to look at the 3 by 3 minors of the matrix. And then we can compute this critical, how many critical points we have. And this number is 31. There's 31 of them, okay? Very good. But over that, when we look at this, there are several information inputted there. The critical points of the variety is there. X tilde is not smooth. X tilde is not smooth. We need only the critical points in the regular part. So we need to remove the contribution of the critical points of X tilde. So we need to compute that. And we can do it by looking at this dimension. So we compute, actually, what we're doing is compute the multiplicity of the singularities. We compute the multiplicities, and it is 7. I didn't put it here, but it is 7. So it is 31, the total, minus the multiplicity of the 2 points. 7 and 7, so 31 minus 14 would be 17 points. So it would be great. For me, I was already very happy that I got the 17 points, fine. But this index is local. We are choosing an epsilon small enough. This is what I told you when we are constructing. I told you we choose an epsilon small enough where this is a non-zero session. So, and this is very, for me, it's very cool. We can track those points. We can see how close they are to the origin. So here we have, this is a report for a function constructed by me and my very dear my friend Marcel. He always knows that when I talk about these things, I will mention Marcel, which is my colleague and a future collaborator, because I had a lot of stupid questions on Oscar, and he was there for me to answer them. So, but what I mean is that in this function, here, these roots are the 17 points that we saw there, that we computed. And I code this function to show us the distance from this point, these critical points, to their origin. And from the 17 that we have, only 2 are close. See? And then you can, okay, you can say, okay, Ellen, but it is not that, this is not that far. It's not, but look at how close this was. These are, okay? So actually, we have a global Poincaré-Nash index, and we have a local one. So the global one, that is something to be defined, is 17, and the local one is actually 2. Okay. We can pursue the same thing, for example, using not omega, as I showed you 2 differential forms, omega and a linear one, right? We can pursue this, make this procedure with this linear one. So I did it the same thing. Here we have the same thing, the Jacobian matrix of the defining functions of the variety, the coefficients of the linear form, and then we can pursue the same. If we compute all the critical points that we have, instead of omega tilde here, we would have DL, only the linear one. This is 18. But again, we need to remove the contribution of the singularities of X tilde. That would be, again, of course, is 14 because it's the same variety. We have then 4. And also tracking where they are in the space, we obtain 2 as index, okay? Right? When you see, when I show in these slides, you see I quote, using function this. All these functions, all these numbers can be computed directly using functions coded in Oscar, all right? But I wanted to show you step by step because it's cooler, right? I mean, it's because we understand better what is happening underneath. This is the theorem that is provided by Anna and myself, where we compute the Euler obstruction of a one-dimensional form using the Poincaré-Nash index, because the Euler obstruction of the differential form, we didn't get actually a geometric approach, or an algebraic formula for computing and so on. So using this equality, we can compute it, right? This I presented backwards when we consider how the history actually went. Because first, I found the formula, and I was super happy. And then I called Anna. Anna, please come. I need to show you something. And then I showed it very excited, and then she told me, which one you can compute it? And I say, neither. I don't know, none of them. But I mean, this is how true it is what Cidinha, I mean, I think is the culture of Cidinha that mathematics can be collaborative. Because Anna asked me which one I can compute, which was none, I could actually compute one of them, these 2, right? So it's pretty cool, right? So if we use these formulas that I showed you, and this example that I showed you again, then we can compute the Euler obstruction of the one-dimensional form, which is 0 in this case. Right? So let's say that, I mean, you were going on the mayonnaise, how we say here in Brazil. You're not paying attention in anything, but maybe you can look now what is happening, everyone who is not paying attention at my pictures, okay? So here we would be, for example, our EIDS. And then this would be the cone, for example. And then here I'm looking at neighborhood of the origin, okay? And these points that appear here, you see, these 5 blue points that we have here, these are the points I wanted to count. The number of critical points in the regular part of the variety. It's not like air bunnies, it's in the regular parts of the variety, sorry. And then what we do is we make the essential smoothing. This would be the represented by this paraboloid, yes? And then what we see is that the blue points, they stay still. They stay more or less where they were. What can happen in the essential smoothing is that these points, this singularity, can split in more singularities. And that is what we need to discount, okay? So this is how this is what I mean by these red points. These points can appear when we make an essential smoothing, okay? Right? An application, natural application will be, look at the case where we have, instead of omega, the differential of a function, of the function. And this is a natural, of course, the way I presented is natural, but also because this is where I came from. This is what I studied always, right? So it's possible to produce examples of the Euler construction of the function using this algebraic or geometric approach, as you will. So I just put here this example. Is a different one. So it's the first element, the first fourfold in the list that we have that is available in the on determinant of singularities. Actually, it's not my list. So here is a rigid singularity. So if you make any smoothing, essential smoothing that we make, you can only move the singularity around. You do not remove it. You do not split. It's only that one. And I took this function and this linear form. All right. So I just quote here that an essential smoothing would be is the variety itself. You cannot do anything. In any case, you can move it. So you change coordinates and go back to that. So this is it. And then we pursue the computations as I explained it to you. Right? We make that big matrix, and compute the 3 by 3 minors because we are in the same dimension over here. So the total number of critical points that we found is 20. We remove the number of singularities, the multiplicity of the singularity, which is again 7. This is not random. It's 7 again. It's not random. But let's see if I have the time to explain. And then we obtain the number of regular, I would say we call regular critical points because it's on the regular part of the variety, is 13. So tracking the singularities, we obtain here 10 of them, which is pretty close to the origin. So the Poincare-Hopf-Nash index of this differential form on X would be 10. Computing the Poincare-Hopf-Nash index of a generic linear form, we obtain 0. And then we conclude the example with the Euler construction of a function being 10. Okay. Okay, this was the result that I wanted to show you, but I wanted to finish with directions of future research. So I wanted to show you a phenomena that I saw, that I recognized using Oscar, okay? So here I am considering this IDS, actually. We have this function, and when we think on a morphification of a function, we have a face for it, right? This is the face, is the function plus t, a small t, complex number t, times a genetic linear form. This is the way we do it. It's pretty close to this one. It's the same idea. Okay, so what I wanted to do was, let's see what happens to these tracking numbers that I told you, the tracking of the critical points, where they are in the space. I wanted to do what happened when t goes smaller. This is my objective here. So I took the function like this, and I deformed with this linear form, and I am taking t equals 1. So when I look, see, it's the same example as I showed you before. When I look at the roots, where the roots are, this is what happened. Terrible. This is the singularities are all around. We don't know. There's none close. Okay. Let's go to the one to that number that I don't know, 100, a very large number, 1 million. So this, look what happens with where the points are. So okay, some went closer, but we don't know which one is really close. It's not clear yet. A little bit more. Look what happened. 10 of them went pretty close to the origin. One is very close, but we have this 10 very close. But see, before they were kind of it was not possible to say which one we need to take, but this one we can say. And 3 of them is like 35. Here we have, maybe I don't know if it's clear. This E minus 5, I'm sorry, I didn't say it, but this means 10 to the minus 5. This is the meaning, okay? 10 to the minus 5. And this plus or less that appear over here that is pretty small is because we are using approximation. We are using computers to do it. So this is why it's more or less this. Okay, this is the meaning. Okay. Then I went to this other number, even closer to the origin. See what happened. We have those they are a bit closer to the origin, but the other ones are going far. They are escaping to infinity, right? No. Yes, they're escaping to infinity. They are almost finishing, right? So what I wanted to understand now, and I mean, the examples are pretty cool in that sense, is can we track all of them? Here I'm using determinant of singularities, but I can use complex analytical varieties, right? So there are papers, I'm sure many of you know, but there are papers working on that, and the examples that what we can see with the computations matches theorems that are available in the literature. So it's pretty cool, and this is another path that I wanted to explore more, right? So this is one direction for future research. So over here, I wanted to show you the main references. So Eblin and Guzenzade here, we have this one with the definition of the Euler obstruction of one form or on a complex analytic variety. This one is the paper on indices for determinant of singularities. Here I approach Poincare-Hopf-Nash indexes, but there are 4 others in this paper, so it's like a mine of gold for many. Here I have this paper where we have the definition, the construction of the Euler obstruction of the function, right? Where there is the topological description for that, construction for that. And this is the preprint, where you can find this formula and some of those examples, right? So we will keep honoring you, Cidinha, and thank you very much for the attention.
Thank you very much, Ellen. Are there any questions or comments?
Thanks, Helen. How do you prove your formula relating Euler obstruction and Poincare-Hopf-Nash index?
Using, in this paper, where they presented where Eblin and Guzenzade present the Euler obstruction, the Euler obstruction of one form, they give a relation with the radial index. And in this paper, in this one, they gave a relation between radial indices and Poincare-Hopf-Nash indices. So it was a matter of reading the both paper and putting it together. The relations are pretty much written up already. Yes.
Any other questions?
Hi, Helen. So in this diagram, in the particular case where X is already a genetic determinantal variety, X equal MTMN, so all the numbers that you defined, they are the same, or?
Yes, now, I'm not sure. This is a case that should be written. I am not sure if they are the same. Yes. I cannot tell, but I can think of it and answer in this week, I hope. Okay. Yeah, but it's a pretty nice particular case. Yes. Good point.
Okay, thank you.
Thank you.
Any other question? If not, let's thank the speaker again. Thank you.
Thank you.
Este vídeo é uma homenagem à professora Maria Aparecida Ruas, nossa querida Cidinha. O que você verá a seguir é apenas uma pequena amostra de uma coleção de depoimentos de colegas, amigos, estudantes, colaboradores e membros da comunidade matemática que tiveram suas vidas marcadas pela presença, generosidade e trabalho da professora Cidinha. Esses registros fazem parte de um acervo em permanente construção, iniciado logo após a sua partida e que continua a crescer. Juntos, eles preservam memórias, experiências e reflexões que ajudam a contar a história da Cidinha, evidenciam seu perfil como uma pessoa em matemática extraordinária, orientadora e amiga sem igual. Gostaríamos de expressar nossa mais sincera gratidão a todas as pessoas que já compartilharam seus depoimentos e contribuíram para a construção deste acervo. Convidamos a todos aqueles que desejam participar desta coleção, compartilhando suas próprias lembranças e reflexões a fazer. Ao final deste vídeo, você encontrará um QR Code com as informações necessárias para enviar sua contribuição. O que apresentamos aqui é um breve recorte de uma coleção muito mais ampla para celebrar a vida, o impacto e o legado duradouro da Cidinha.
Mas o problema é que, mesmo para discutir matemática, não tem que estar muito coisa. Eu conheci a professora Cidinha em 1945, quando eu cheguei aqui no CNC para fazer o mestrado. Eu fui conversar com ela sobre orientação. Ela me atendeu super bem, né? Muito solícita, e eu acabei decidindo trabalhar com ela. Ela falava de geometria e de singularidade de uma forma tão simples, tão leve de se fazer, que você fica muito cativada, né, no assunto.
Lá na graduação, eu tenho experiência com psicologia, então tem um pouco mais próximo, falar depois do que eu fazia, ela sempre teve uma hora que eu apaixonei, a forma como que ela trazia tudo, e ela, o conhecimento dela de matemática é muito vasto, né? Então, conectar com outras coisas, ela sempre trazia os temas de uma forma diferenciada, né? E a professora aprendeu com muito, né? Da coisa de singularidade, que é onde você aprende tudo, né? Onde você toca em várias áreas, né? Ao mesmo tempo que você pode colaborar com pessoas de áreas distintas, que eu não conheço assim, indivíduos de áreas.
Fui aluna no IPNC, de doutorado, e na época eu fiz curso com a Cidinha, fui como professora no curso de variedades, e aí então eu fui lá conhecer. A Cidinha foi uma das melhores professoras que eu tive no IPNC, ela foi muito didática e muito atenciosa para os estudantes. A Cidinha fazia distinção, onde o estudante tinha ao mesmo tipo de importância que o pesquisador que já estava lá no final da sua cabeça. Então, ela sempre aquela professora que inspirava a gente, né? Tanto a querer saber mais, a buscar conhecimento, como também a olhar e dizer, nossa, é esse tipo de profissional que eu quero ser.
É um número muito típico da Cidinha, em cada um dos indivíduos como um indivíduo. Eu acho que ela até conseguiu numa sala de aula de 30, ela conseguiu lidar com 30 indivíduos. Isso é uma coisa muito importante. Você faz um trabalho melhor, quando você faz esse trabalho assim. Ela tinha horários certos para trabalhar com vários alunos, horas marcadas, hoje das tantas é esse aluno, das tantas é aquele aluno, agora das tantas é Isabel. Ela conseguia fazer, concentrar o trabalho que cada um deles estava fazendo com ela, que eram coisas bastante diferentes da gente.
O meu encontro mais destacável da minha relação com a professora Cidinha foi a primeira vez que eu cheguei aqui, a São Carlos. Então, naquela época, eu tinha uma orientadora, a Carmen. A Cidinha e a Carmen eram muito próximas, elas eram quase como irmãs. E aí a Cidinha estava organizando o primeiro encontro de singularidades, que era o ano 1990. Aí conheci a Cidinha, ela começou a perguntar o que eu estava fazendo, aí então ela quase que me obrigou para dar uma palestra naquele. Eu estava morto de medo, mas ela me encorajou muito para fazer isso. Ela tinha essa virtude, não, para se interessar muito pelas pessoas, mas era de verdade, não era uma coisa só para fazer o protocolo, não, mas ela realmente se interessava. E toda vez que eu esteve aqui, ela sempre tinha essa coisa de falar com todo mundo para que a pessoa sentira que ele era o principal convidado, não? Então ela tinha essa virtude, essa capacidade, não?
Uma palestra, a Cidinha estava lá, terminando minha palestra, ela aproximou do canal, e nossa, foi falar, discutir, e depois o seguinte, nós ajudou. Então, uma colaboração muito interessante, muito enriquecedora matematicamente, mas também mostrava muito essa personalidade da Cidinha, e sempre era muito empática, sempre sabia falar do coração, e chegar ao coração. Muito curiosa. O que acontece comigo? O que acontece comigo? E o que passa aqui? Sempre sendo ponto, discutindo com outras áreas da matemática. Muito interessante. Então, foi muito bonito. O fato de fazer as pessoas sentem que era, muitas vezes, já foi uma pessoa que você podia falar, e ela se retirava. Entendeu? Deixa as pessoas discutir junto. Isso é uma qualidade incrível dela. Quando eu conheci esse grupo pela primeira vez, eu diria que foi por volta de 1989, mais certamente 1990, quando eu fiz o primeiro workshop, né? Foi feito o primeiro workshop que se fez em São Carlos. Esse contato que eu fiz no workshop, o que marcou foi muito a gentileza do Cidinha, né? Preocupada na viagem, se eu queria ir de ônibus, se eu queria ir de avião, e toda a logística que ela sempre. A gente ela faz isso com todos os visitantes aqui do CNC. Eu sempre estava envolvido não só com pesquisa, às vezes as pessoas saem só com um aspecto da carreira acadêmica. Né? Mas o dia é sempre preocupada com a formação de alunos, né? Eu não sei quantos alunos ela formou. O que eu sei que eu participei de várias bancas de alunos, tanto mestrado quanto doutorado. Consegui fazer uma palestra que se não me deu de singularidades, que eu ainda era um aluno de graduação. E eu entrei na palestra e a Cidinha começou justamente com uma frase que é: a matemática é mais do que competição, a matemática é colaboração. Essa frase dela, ela assentou no meu coração, nunca mais foi embora, à medida que eu fui tendo mais contato com ela. Porque essa cooperação, essa gentileza, esse carinho, esse amor, não só pela docência, mas pelas pessoas da Cidinha, essa frase era traduzida em cada momento que ela interage com as pessoas. É uma coisa que, provavelmente, colaborar mais do que competir. Em vez de competir, colaborar. Competir, sim, pode ser interessante, mas colaborar melhor. Mas ela tinha isso num nível muito alto, muito particularmente.
Eu acho que a matemática é mais, isso é mais valorizado, não? O fato de ter colaborações com outros grupos, porque a gente não tem laboratórios, não? Então a forma de fazer pesquisa é discutindo com outras pessoas e mostrando o que você faz para outros, para eles concordar se o que você fez está certo ou não, e para ter novas ideias de como progredir no assunto.
que tener una capacidad de trabajo y una visión de las cosas muy especial para mantener el tirón de este congreso durante más. Yo creo que eso tiene muchísima mérito. La verdad que estoy muy agradecido a usted porque este congreso de alguna forma sí, es una manera de mantener vivas muitas vezes muitas vezes. Muito legal. Ela participa das palestras, das apresentações e sempre tem uma pergunta inteligentíssima, uma pergunta feita de uma maneira tão carinhosa, tão interessada, que naquele momento você se sente o medalhista Fields, né, apresentando.
Por ejemplo, todo el Congreso, y todo el hacer para esta, son difíciles, por ejemplo, él, así experiencias, es difícil el Congreso, no da las de experimentos por allá, las oficinas, no siempre fue preguntas, era eso, eso fue difícil también.
Como funcionários, Cidinha fazendo muitas perguntas finas que precisa.
Nessas áreas de visitas, convívios que nós tivemos, além de aprender matemática com ela, aprendi muito como ser matemática de liderança. Nossa maneira de lidar com relações de trabalho com as pessoas. Então, ela tem um conhecimento importante profissionalmente.
Principal, a questão humana. A Cidinha, além de ela ser uma excelente pesquisadora, ela existia todos nós, mas mais do que isso, ela tinha um lado humano que é incrível.
Não é ironia, nenhuma na foto na pessoa singular. Para mim, ela tem que ser mais do que uma mãe, uma pessoa muito amável, humana. Ela é excelente em colaborar.